Hello, in this video we're going to see how the variational solution of the H2 plus molecule in the mean field approximation leads to the formation of energy levels. And we're going to also see how these energy levels change as we change the bond distance between the two atoms. So let's start with the student learning objective. We want to interpret the bonding and anti-bonding solution that arise from the linear combination of atomic orbitals treatment of H2 plus. We want to interpret the coefficient signs and the energy splitting relative to the atomic energy. So let's see where we are starting from. We are starting from the expectation value of the energy, which we found was described by this equation with terms shown here. So the matrix element HAA and HAB involve the atomic orbital centered on A and B through the electronic Hamiltonian and give rise to what are we calling Coulomb and Coulomb integral J and resonance integral K. And then there is the overlap integral between these two 1s orbitals on A and B that is given by SAB. All right, so we take this equation, we apply the variational method, so we are trying to minimize the energy by changing the variational parameter Ca and Cb. And for simplicity, here we are keeping theta, the nuclear charge on those orbital coefficient, fixed at 1, which is what it would be in the hydrogen atom. If we allow it to float, we can even get a little bit smaller energy, but for simplicity of treatment, here we are fixing it at theta equal 1. So when we do that, it turns out that in order for the solution of this equation, the minimization of this equation of the energy, not to lead to unrealistic results like the wave function doesn't exist at all, something called like the secular determinant, if you read it about it somewhere, arises. And by tinkering with that secular determinant, it turns out that two energy solutions that minimize the energy are available, are possible. One in which the two coefficients Ca and Cb are the same. So Ca equals Cb. We put those coefficients in there and we minimize the energy and we get an energy which we label epsilon plus that has this form. And then another valid solution that also doesn't make the wave function disappear is when the two coefficients have opposite signs. So Ca equals minus Cb. We minimize the energy. For that case, it's going to be a different energy than E plus, and this E minus has this form here. So two different energy solutions for two different combination of the coefficient that we place in front of the 1sa and 1sb atomic orbitals. All right, so let's see some numbers here. So let's fix the distance between these two nuclei at 2.5 Bohrs. And by the way, for all this video, I'm using atomic units, so distance are in Bohrs, energy are in R3, charges are in atomic charges, and so on and so forth. So at 2.5 Bohrs, we have that the energy of a hydrogen atom is negative 0.5 H3. No big deal. We know that that's the energy of a hydrogen atom, wherever we place it. The repulsion energy between the two nuclei, we calculate 1 over R, is plus 0.4 H3. So that tells us that, of course, it's two nuclear charges positive, it's destabilizing at short distances. And then we have to calculate this overlap integral, this Coulomb integral, and this exchange integral. And for this special case of hydrogen 2 plus, they are simple enough that we can calculate them analytically, with just pencil and paper basically. And it turns out that these are the values. These J and K are H3s, and S is just an overlap integral. So we can calculate this number, bottom line here. And then we put all these numbers together to figure out what the value of this matrix element HAA and HAB are. We take these values here, we plug them in here with this EH, and we get these values for HAA and HAB. We take these numbers, we put them back here into the two solutions for the energy, together with the overlap. And I forgot, we also need to ensure that the wave function is normalized. So once we figure out the overlap, we can always normalize the wave function so that the integral over all of the space of the probability of finding the electron is 1. And so we figure out that the energy of the E plus solution is negative 0.96 Hartrees, and the energy of the E minus solution, for the moment we're calling them that, is negative 0.69 Hartrees. All right, big deal. What do they mean to us? We need to compare them to what? To the energy of the species that are coming together to form the molecule. And what are these species that come together to form the molecule? Well, we have H2+, so one of the species is going to be just a hydrogen atom, for which the energy is negative 0.5 Hartrees, and the energy of a proton alone in the universe at infinite distance from the hydrogen atom is going to be 0, because we have a proton, a positive charge, just by itself. So the reference system that we are comparing our energies to is negative 0.5 Hartrees, the energy of this system at infinite distance. So in order for the species H2+ to be stable, we need to be lower energy than that. All right. We forgot one thing, though, when we calculate this energy. Not that we forgot, we knew that we didn't put it there yet, because we were only looking at what? At the electronic Hamiltonian. We said, oh, we are going to set aside the nuclear repulsion because it's just going to shift the energy up by a constant. Well, that is the constant, the energy repulsion between the nuclei, that I need to add to these two electronic solution for the energy to have the real energy. We're calling this energy for the ground state. We're labeling it Eg, and G, we're going to see it comes from the German word gerade, which means symmetrics. So we are summing this E plus this repulsion energy, and that gives me this negative 0.56 Hartrees. And look and behold, I compare it to that one, it's more negative. What does it mean? It's more stable. H and H plus, therefore, are gonna come together and drop into this lower energy state that is just a little bit lower, but it's definitely lower in energy than that. So then let's look at the E minus energy. When we sum this nuclear repulsion, that's the energy that we're getting, negative 0.29 Hartrees, which is higher in energy than the two separate species. So this is the excited state energy, and we're going to label that EU, U for German again, ungerade, which means anti-symmetric in a way. And that tells us that if we put the electron on this molecular orbital here, it's going to dissociate in the separate species because it's higher energy than the reference system. All right, so lots of talking looking at these numbers. Let's try to look at the visual of this system to maybe better understand what's going on. So here I have the zero energy. On the y-axis, I have the energy. Zero is the energy of the three separate species at infinite distance. One electron, one proton, and one proton. We know that an electron and a proton can come together spontaneously and form a stable hydrogen atom that has negative 1/2 Hartrees energy. So this is going to be actually our reference system, as we just agreed, this negative 0.5. So we're going to have our two theta, theta A and theta B, that we are using 1s-like orbitals. So that's what I'm showing here. These are the two 1s-like orbitals that we are starting from. And when we are mixing them to form the ground state, ground state molecular orbital, we are mixing these two orbitals with Ca equal Cb. Remember, that's what are the two solutions. So they come in with the same sign. That's why I drew them with both the same color, because 1s has only one phase. And so I drew them with the same color because Ca equals Cb. You can choose them to be both positive, both negative, doesn't matter. All right, we form this molecular orbital, and the corresponding energy of that molecular orbital, we already figured out, is a little bit more negative than the separate species. So it's ground state, the molecule is stable there. The opposite case arises when we combine these two orbitals with opposite sign. Ca minus is equal minus Cb. So that's why I changed the color here, because I'm changing the sign of the beta, of the B, in this case, orbital. And so in this case, in the ground state, the two orbitals are combining what we call the same phase, in phase. And here they have opposite signs, so they are combining out of phase. That's the appropriate way to call them. To form what? An anti-bonding orbital, phi u, where again the sign of the two orbitals here is opposite, whereas here had the same sign. And notice that this orbital here is quite higher in energy than where we started from. So again, our reference here is what? Is this negative 0.5 line. So what we care about is how much more stable or how much are we less stable than that in these orbitals. So we are taking this difference here by this gray line, and that is delta Eg. It's negative 0.06 Hartrees, but it's still a relevant number when you convert it to kilojoules per mole, for example. This is what is the stabilization energy. This is how much more stable the H2 plus system is when we compare it to the separate system H and H plus. And conversely, this delta EU is telling us how much less stable the anti-bonding system is, the anti-bonding level, the excited state energy is with respect to the reference state. Notice that this anti-bonding orbital EU, actually the delta EU, is bigger than delta EG when we look at it in absolute sign. What does it mean? That the anti-bonding orbital EU is more destabilizing than what the bonding orbital EG is stabilizing. And that doesn't seem to be a big deal at this moment, but it's going to be extremely important when we look at the stability of electron configuration, when we start filling bonding and anti-bonding orbitals. It's important to remember that anti-bonding orbitals make the system more unstable than what the bonding orbital make it stable. Alrighty, last step here in this process is to look at how these energies change as a function of the bond distance. So we want to interpret how molecular energy levels and integral values for H2 plus vary with the internuclear distance, and identify the factors that determine the equilibrium bond length. So again, we start with our reference, EH negative 0.5 Hartrees, and here I'm drawing a vertical line. This is on the x-axis, we have the bond distance. I drew a vertical line at 2.5 Bohrs, which is what we were using. And on the y-axis, these numbers are either energy or in Hartrees or overlap, depending on what we are plotting. So let's start plotting the overlap integral SAB. We see that when the two atoms are big distance, the overlap integral is going to be very small, and it's going to go to 1 when they are overlapping. No wonder there, that's what a normalized atomic orbital should have. So when the two atoms are perfectly overlapping, we're never going to get there, we expect it to be 1. So that's the shape of the overlap integral. Then the repulsion energy V and N between the two nuclei is small at large distance. It's positive, and it becomes big and positive as R goes down. And so it's going to go to infinity as R goes to 0. So it's going to blow up real quick there. And so that we're going to see is what prevents atoms from collapsing onto each other. Then we plot this ground state energy that at 2.5 Bohrs we found that it was down right there. And, oops, right there. And we see that as we go to long distances, it basically goes to 0. Why? Because we are approaching the system from which we started from, H plus and H. And as R goes towards 0, at some point it's going to just take off and go up very quick because it's following this VNN that is also taking off super quickly. We look at the other solution, the anti-bonding orbital, and we see that it's the potential, what we call, is always repulsive. Here in the ground state, we saw that there was a dip forming. So if we think in a way of dropping a ball on this blue curve, we can think that the ball is going to find its place down there. If we place a ball like the H2 plus on this EU curve, it's going to just continue going until it reaches infinity. And so that curve, the anti-bonding curve, is indeed anti-bonding. It leads to the molecule to break up. And the EG solution is this bonding, because if I populate that orbital, the system is going to stay there, because going anywhere else is going to increase its energy. The distance, the energy difference that we have already seen from the reference and the bottom of this well is the delta EG, the stabilization energy. And the last thing that we're going to look at are the negative of the Coulomb and of the resonance integral, J and K. I'm taking the negative because in the formulas where they are used, they come in with a negative sign, so they are both stabilizing. And so we see that they both have this stabilizing effect, negative energies. One note that we want to keep in mind, and that's the last thing of this video because before we look at the summary, is that when we dissect all of these energy terms in terms of J and K and whatnot, it turns out that the Coulomb integral J, yes, it is stabilizing with respect to the separated species, but it stabilizes, in a way, both the ground state and the excited state the same level, the same amount. The resonance integral K, instead, is what is actually contributing to stabilizing this little bit more the ground state, EG, and not so much the excited state, EU. So, in other words, it is the exchange integral K that is responsible, really, ultimately, of the last push for the bond formation. And that's important to keep in mind, even if we didn't look at the equation, because whereas in this hydrogen 2 plus system we could attach a simple understanding of that resonance integral K as the electron density given by the overlap of the two orbitals interacting with either one or the other of the two nuclei. In molecules that have more than 2 electrons, that integral cannot be interpreted in such an easy way. It turns out it's going to be a purely quantum effect of some exchanged density that either interacts with one or the other atoms, and it's not something that you can so rationalize in such a nice way. So that is important to at least appreciate that the real reason for bond formation lies in this resonance integral K, which is a pure quantum mechanical effect that doesn't have any counterpart in classical physics. All right, let's wrap it up with a nice summary. So what did we learn? That within the Born-Oppenheimer approximation and in the Millfield approach, the Schrödinger equation for the H2 plus molecule can be solved using the variational method. We didn't see how we solved it, but we saw that it can be solved. 2 solutions emerge from that solution. One in which the 2 coefficients are the same of the 2 orbitals, and so we label that solution EG, and we call it bonding. And another one in which the 2 coefficients have opposite sign, we label that EU, and it's anti-bonding. EG is lower in energy than the 2 separate species, so it means leads to bonding interaction. And we call the type of ways that the atomic orbital interact with each other in this wave function, in this orbital, they overlap in phase. In the other case, in EU is higher in energy than the separate species, so it's anti-bonding. And in that solution, the atomic orbitals interact and overlap out of phase. We also learned, and that's important to keep in mind, that the anti-bonding orbital EU is more destabilizing than the bonding orbital EG is stabilizing. Remember, that's important for when we look at many electron atoms and many electron molecules and electron configuration of them. Further, we scanned these terms over the bond distance, and we confirmed that the ground state leads to a dip, a minimum, so we confirm the bonding nature of the bonding orbital, and we confirm that the anti-bonding orbital instead leads to the separation of the molecule. And we also looked that at short internuclear distance, the repulsive term VNN dominates and skyrockets, and so that's what prevents the two atoms to go on top of each other. And finally, we appreciated that the resonance integral K is actually what is the ultimate key contributor to bond formation.